Okay, guys. Right. So it's 9 a.m. Okay, 9:01. So let's continue. So we started in the previous classes making a transition from vector quantities to scalar quantities, right? So that's the major point in the last several classes, right? And in order to simplify our life in terms of calculations, right, it's much pleasant to work with scalar quantities than vector quantities. And in the previous class, we replaced first, we made the first step. We replaced a force, which is the vector quantity, with the potential energy, which is a scalar quantity. And very important, both of these quantities describe exactly the same thing: interactions between charged objects. Force describes interactions from the point of view of vector quantities. Potential energy describe exactly the same interaction from the point of view of scalar quantities. And now we need to dive slightly deeper. Now we need to replace the electric field. All right. So, for example, let's say you have some object, which charged object, of course, charged object, which creates an electrical aura around itself, right? And before, up to this point, we were describing this aura using the electric field. It's just our way of modeling, of describing electrical aura created by a charged system. And now we are ready to introduce an alternative way of describing exactly the same electrical aura using scalar quantity, which is called the electric potential. Again, the key point is exactly the same electrical aura, and now we can describe this aura using either electric field, which is the vector, or electric potential, which is a scalar quantity. So that's the goal of today's class, and that's what we're going to practice today. Electric potential. So now, guys, be careful, because they sound like similar. Potential energy, electric potential. With time you will get used to, right? So those are two different things, right? Potential energy and potential. Okay, so now how should we introduce this electric potential? And in order to do that, let's recall how we introduced the electric field, right? So electric field was introduced in this way. So you remember, of course, we used E, and we would measure or calculate force acting on a probe charge. You remember that small positive probe charge, and we would divide that by the value of the probe charge. So that's how we introduce the electric field. And look at the structure of this introduction, of this definition. Force, it's a quantity, of course, vector quantity, which describes interactions, and divided by the probe charge. So now you should be able to guess how we should introduce the electric potential. Structure must be very similar, except for, instead of vector quantity, which describes interactions, we're going to use the scalar quantity, which describes interactions. Instead of force, just use potential energy. And the rest of the structure, structure of the formula will be the same. So we will take, now instead of force, potential energy, describes interactions, and divided it by the value of the probe charge. So you see, structure of the definitions are the same, except for there we have vector quantities, now we have only scalar quantities. So it's easier to remember if you have connections, and you see the structures are the same. So now I need to frame it, of course, with red, because it's new. So that's how we introduce the electric potential. That's basically, you see, I put 3 lines. I drew 3 lines, so means by definition. So now we introduce the new quantity, electric potential. And of course, the question is, should we introduce the special unit? Because you remember that discrimination about the electric field, important quantity, fundamental, but it doesn't have units. But the electric potential, it has a special unit. And the reason is because everyone, right, who are somehow connected to science, right, uses electric potential, right, starting with technicians, engineers, experimental physicists, right, except maybe theoreticians, they don't use electric potentials, right, they work with electric field, but the rest of the world uses electric potential all the time. 9-volt battery, potential, right? So since lots of people use it, of course, special unit was introduced, volts, right? Units of the electric potential, volts. So then, so now we introduce in general, so of course this definition can be used to find the electric potential created by any charged object. And again, the difference, in order to introduce potential energy, we needed two objects interacting, right? Because it's energy of interaction. Potential and electric potential is just a quantity which describes that electrical aura which is created by one object. So now, in order to so we just need to one object, right, in order to create electrical aura, and of course we can describe that aura using electric potential, right? So only one object is needed. Right? Okay, so so let's start with uh, a first system, and probably you should be able to guess which systems we're going to discuss. Right? Parallel plate capacitor. Of course, it creates its electrical aura, and again, that aura can be described either this way. We know how to do that this way. And now we need to introduce the electric potential, right, inside of the capacitor. And the second object, point charge. So pretty much all the time we will be playing with capacitor, point charge, capacitor. So a parallel plate capacitor, PP capacitor, right? Probably I will draw the picture. Yeah, right. Something. Okay, I need to start making my pictures smaller. So let's say minus, 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 and this will be positively charged electrode. Of course, there will be electric field lines. That's the old way of describing this aura. But now we need to derive the formula which would describe electric potential inside of the capacitor. Okay, definition is here, so let's just apply it. All right, so V equals U over Q. And you remember from the previous classes, and I derived it in the lecture, in the previous lecture. Potential energy of a probe charge inside of the capacitor is Q E S, and now divided by the Q, right? So you see, this probe charge, of course, disappears, and we're getting the formula. So there's no even derivation, just the trivial manipulations. Right. So E times S. So as a result, I can write over here, so V equals E times S, and frame it because we are going to use it quite often. So that's the expression which can be used to find the electric potential inside of the capacitor. Look at the structure. E is constant because we're inside of the capacitor uniform field. S measured from the negative electrode, right? So S measured from the negative electrode. This is D, right? So now, next question, of course, logical. Of course, electric potential is not visible, right? And of course, it's useful to come up with some lines which can be used to visualize this aura. But of course, now using in terms of electric potential. So which lines can be used? Okay, people decided to use what is called equipotential lines. Equipotential lines. Pretty much lines where points are at the same potential. V is constant. Lines along which The electric potential is constant. So now let's try to draw electric field, equipotential lines inside of the capacitor. Again, V must be constant, right? So this V constant, electric field inside is constant, and S changes, right? So if S is constant, then V will be constant. S constant, it means that, for example, if you take this S, some arbitrary S inside this, so all these points are going to have exactly the same electric potential. So it means that this line parallel to the electrodes is an equipotential line. Okay, let me draw a dashed line. So this is an equipotential line. And of course, I can draw as many as I want. So these are equipotential lines. Okay, probably I will show something like this. So these are equipotential lines. It's if you draw a two-dimensional picture, if you imagine three-dimensional situation, capacitor three-dimensional, of course, we will have to talk about equipotential surfaces, right? It's a surface, points of which are at exactly the same potential. For example, this may be on 1 volt, all these points are at 2 volts potential. Right? Then so that's what we can use to visualize electric potential. Then potential difference. Of course, you've heard, right? 9-volt battery, what is that? It's just a potential difference between two electrodes of the battery, right? Potential difference. In this case, we can calculate potential difference or sometimes voltage, potential difference between these two electrodes. Potential difference across a capacitor, delta V. Of course, it will be V of electric potential at the positive electrode minus electric potential at the negative electrode. So what's the electric potential at the positive electrode? Look at the formula. At the positive electrode, as S equals to D, E is constant, some given constant, right? If you charged it, so E is basically determined. So it will be E times D. But at the negative electrode, here, S equals 0. So the electric potential is 0. So it will be E times D minus 0 equals to E times D. So occasionally we will use it during this semester, that the potential difference across a parallel plate capacitor is equals to the electric field times the spacing between the electrodes. Right? So from time to time we will use it. I'm not framing it, but we needed to mention it. So, okay, maybe I will write here. So V equals to ED, and of course here, V equals 0, right? So basically, since we can talk about the reference point for the potential energy, we can also talk about reference points for the electric potential. So this is our reference point. Okay, so that's the capacitor. Now the second system, point charge. So now point charge. And of course, we need to introduce the formula expression, which can be used to calculate the electric potential around point charge, at any point around point charge. Right? So again, here's the definition. V equals U over Q. Right, so V equals U over Q, and potential energy. We derive the formula, right? Again, so what's the situation? So if you have point charge, let's say Q capital, which creates an electrical aura, right? So this is the electrical aura. And you take a small positive probe charge, position it there, calculate this potential energy between these two charges, and divide it by the value of the probe charge, right? So it's a K Q small times Q capital divided by R and divided by the value of the probe charge. Of course, this disappears, and we're getting the formula which we are going to use, of course, more often. Right. Yeah, probably first let me continue this line. KQ divided by R. Right. Okay, probably I will write it there and frame it. So V equals KQ divided by R. Right. So electric potential created by point charge Q capital at the distance R from that point charge Q capital, right? So maybe I should also show that this is R, right? So yeah, we introduced. Okay, so now the next question, equipotential lines. Here, yeah, we have these parallel lines. But what about equipotential lines created by a point charge? Again, the same analysis. Look, V must be constant, right? V must be constant on an equipotential line. So V constant, K constant, Q constant is given. So in order to get V constant, R must be constant. R constant, what is that? It's a circle. Circle around the charge, of course, centered on the charge. Okay, I can draw, of course, um, equipotential lines. Equipotential lines are circles. Again, these are points where V equals constant. Right. Maybe I can draw. Probably I should have recycled this picture, but okay, let me draw it underneath. So if this is charge Q capital, and then, of course, again, that aura can be described either using electric field. Let me draw both. Right, so electric field lines, we can describe this. But again, it's our old way of describing this electrical aura. Now, new way, electric potential, and of course, equipotential lines are circles. So these are equipotential lines, those greenish lines. Of course, you can draw as many as you want. Right? So you can take any point on this line and electric potential will be exactly the same. Let's say 1 volt. Then probably another thing. Let me plot this electric potential created by, for example, point charge. Let's say positive point charge. Let's say we have plus Q. And I want to plot this is V and this is R, distance from the charge. If electric potential created by positive point charge, then of course electric potential has a spike at the charge and then it goes to 0 when R goes to infinity. So as a result, we will be getting something like this. Right, so this will be the plot, how the electric potential changes or decays as you move farther and farther away from the point charge, which creates this electrical aura. But if the charge is negative, if a charge is negative, let's say minus, so that's Q. And now let me plot also something similar. Wait, no. This is V, right? So in this case, charge is negative, so the electric potential is negative and goes to 0 at infinity. So it will be something like this, and spike at the charge. Right. So why I drew it to emphasize that points around positively charged object is at higher potential than points around negatively charged objects all the time, because here potential is positive and here potentials are negative all the time, right? Then Okay, somebody posted something on the chat. Looks like. No, it looks like nothing important. Right. So then, the last piece before we start, let me check moving into the problems. Uh, Look, now let's imagine that you have electrical aura created by something. And let's say you know information about the electric potential at any point, electric potential. And now let's say some charge flies, so some charge is exposed to that electrical aura. And the question is, how can you find potential energy of that charge inside of that electrical aura? And the answer is very simple. Just solve this formula for U. U equals Q times V. It's the same like here. You remember in the past when we wanted to find the force if charge is exposed to the electric field, we would just solve it for F. F equals QE. Now U equals Q times V. Okay, let me write it underneath over here. Let me separate it something like this, right? And all right, U equals Q times V, right? Okay, so it's we will use it. We will use it quite often. Again, if you know information about the electric potential at the point where the charge is, multiply them, and that will be the value of the electric potential energy. Okay, so that's what we needed to start solving problems. Again, uh, basically, usually I discuss that in the lecture, but since the next lecture will be only tomorrow, and we needed this, so I had to do it in the recitation class. Okay, if you have questions, go ahead. Otherwise, we'll start discussing problem 2516. It's still chapter 25, 16. And here's the situation in the problem. Okay, let's imagine this silly situation, right? Let's say my neighbors got angry with me writing on the wall all the time, right? And let's say they start shooting electrons at me. Just completely silly, crazy situation. And so let's say I want to protect myself. Of course, walls here are basically board walls. It's useless. They're useless, right? All right. So of course I will try to create some electrical aura, right? Of course we can, in order to stop those electrons. And of course we can describe that electrical aura either using electric field, but that's in the past. We don't want that, or using the electric potential. So I want to describe it using electric potential. And I want to answer the question, first conceptually, and then we will calculate. Should I create this electrical aura in such a way so that here by the wall, electric potential would be lower and here higher? Or here electric potential is higher and here lower? So basically we need to answer the question, should delta V be positive or delta V be negative in order to stop electrons from flying into my room?
Positive, right? Because you don't want it to repel.
Okay, you already tried to analyze quickly, conceptually, and answering, right? But I need to be, let's discuss carefully, right? Because if you just answer it like this, chances that you can make flip a sign kind of high. So let's carefully analyze the whole situation, right? But I heard you, right? So we have an electron. So we have electron, and it flies with initial velocity v. Which way I label it? V naught. Yeah, V naught. 500,000 meters per second. It's a 500 kilometers per second. Oh my God! Right. And we want to stop it. We want to stop it. And In part A, let me draw part A. So delta V, should it be positive or negative? Positive or negative? Okay, and I'll put a question mark. Okay, now let me draw the picture. And then we'll start discussing. So let's say this is my electron, right? Minus. Okay, E minus, right? And it flies this way. So that's initial velocity V naught. And of course, what we want to stop it, right? So of course, it will fly for some time, right? And then it stops for a moment somewhere, and then it will start flowing in the opposite direction. All right. So something like this. So that will be its trajectory. And yeah, first let me write it's here. We need to answer conceptually. Conceptually. And then next part B, we will calculate everything, right? Everything will pop up automatically from calculations. Okay. Book offers the table 25.2. So if a charge positive, in order to slow it down, potential must be positive, or negative speed in order to accelerate. No. When I saw this table, I closed the book immediately. No way, right? I will never even try to remember that silly table. I don't want to use the harsher word. Because we need to remember fundamental stuff. And then using that fundamental stuff, we should use some logics, analyze situation. We should be able to answer most of the questions, right? And that table is, no, right? It's not something fundamental. Okay, so my analysis will be based on two simple ideas, which most likely no one can forget. First fact, like charges, of course, we remember, repels, or like charged objects. Oppositely charged object, of course, attract. It's a first piece of information we're going to use. And the second, over here, I mentioned that any positively charged object, points around any positively charged object are at higher potential than points around any negatively charged object, because here potential just positive, here potential negative. I think it's obvious, right? So these two pieces of information should be enough in order to answer this question conceptually. Let's do it. So first, what we want to stop it. We want to slow it down. Electron flies that way. So it means what should be a direction of the electric force if we want to slow it down, if we want to stop it? Of course, it should point in the opposite direction. I think you don't have any doubts about that, right? So that's what we want, right? So this should be the force, right? Okay, let me write. So we want, that's what we want. We want the force pointing that way. In that case, electrons will be slowing down and eventually it will stop. Now, of course, this is the electric force. Of course, it comes from the electric field, right? Which is created probably by some object. We're trying to answer this question conceptually. Of course, analyzing it conceptually, it's easier to use uniform electric field, right? It's easier to use something, the easiest possible situation, right? So let's imagine that here we have some uniform electric field created by an imaginary capacitor. Just imaginary capacitor, right? So of course that imaginary capacitor, right? Let me use some greenish, right? So we'll have some electrode over here and some electrode over there. So let me emphasize, it's an imaginary capacitor, which creates the electric field, which creates the electric potential, right, and so on. And okay, why not? So now we need to answer the question, should this electrode be positively or negatively charged in order to create this force? acting on that charge on that electron. Obviously, so these should be positively charged, because positively charged object and negatively charged object, of course, they're going to attract. Right? So these will be, of course, positively charged. Right? And of course, this will be negatively charged. Right? And so now the last piece, if this is all positively charged, electric potential should be higher. This is negatively charged, so over there, electric potential should be lower. So as a result, we can conclude that here, right, it's a these are initial point, because electron travels from this region to that region. So these are initial points, these are final points, right? So I can write as a result, V initial is sort of, let me write, higher. And here, V final is lower. As a result, delta V, we can easily answer. So as a result, let me continue using green, because sort of green is sort of like my speculations. As a result, I can say that delta V is, which is of course V final minus V initial, lower minus high, of course negative. So again, let me repeat. So that's the conclusion, right? So for part A, delta V, so I can answer, so delta V must be negative to stop it. Again, it might look longer, speculations, but 2 steps effectively. If you want to slow it down, force must be that way. If you want to accelerate it, of course, force would be that way, right? So, but we want to slow it down, so force that way. Then imagine immediately after that some capacitor which creates the field, and of course electric potential. And then in order to get this force, this electrode must be positively charged. It means that points around positively charged object must be at higher potential. Of course, there should be, of course, negatively charged, and of course, those points will be at lower potential. As a result, delta V is negative. Right? So you see, what 5 minutes ago somebody answered, so it should be positive, right? Actually, it's negative, right? So you have to carefully, even sometimes you're really confident, still it's better to, unless you are really super confident, right, and you've done this analysis very often or something similar, right, then of course can answer. So in this case, delta V is negative. So that's conceptually, that's how I would suggest analyze it, based on 2 simple things: opposite charges, oppositely charged objects attract, and any positively charged object has higher potential than any negatively charged object. 2 things. You can wake me up in the middle of the night and I would be able to answer, I would be able to tell those 2 pieces of information which I just mentioned. Of course, I will be very angry, right? But that's its second story. All right, so part B, now let's calculate it all. Let's calculate. Calculate delta V. And of course, that minus will pop up automatically from calculations. Okay, all right, so which approach to use? Now we have 2 approaches. You can use either force approach or energy approach. And I told you they're equally strong, they're equally great. But which one will be easier here? Since the question is about getting some information about the electric potential, right? And the electric potential is directly connected to the potential energy through this formula, right? It's a clear indication that our energy approach will be easier, because immediately you can introduce potential energy, use conservation of mechanical energy. That will be easier. All right. So if the question about electric potential or some information about the electric potential is given, most likely that the energy approach would be the easier one. Okay, so let's use the energy approach, right? And I will put symbol 2, and let's use energy approach, which is based, you remember, conservation of mechanical energy. I will write so E initial equals to E final total mechanical energies. We just need to compare, and let me emphasize, so this is of course our initial point, and here of course our final point. And of course we can add additional piece of information. At the final point, velocity is 0 because that's the turning point. It stops for a moment, right? So over here, v final equals to 0. It stops for a moment. Okay, so now let's write explicitly. Of course, it will be k initial plus u initial equals to k final plus u final. Of course, expression for the kinetic energy gap. Kinetic energy, everyone remembers, 1 over 2 mv squared, and immediately k final is 0 because final velocity is 0. So I'm not going to write that. I will dump it immediately. And okay, at this point, I've seen in the past quite a few students on the final exam would get stuck. They forget about this. Not everyone, but I've seen like maybe 5-10% students sitting on the exam trying to figure out what to do next. No, you just need to connect the electric potential with the potential energy, which is U equals QV. They just forget about that. Okay, let me frame it again with red because. And again, it looks very similar like when we introduce electric force. F equals QE. Now U equals QV, right? Okay, so now let's plug it. 1 over 2 mv naught squared, so that's initial kinetic energy. U initial, let me move it to this side. So of course it will be U final minus U initial, and let me plug instead of U, QV. So it will be QV final minus QV initial. Q can be factored out, and we're getting the our unknown delta V, because delta V, you remember, it's a final value of potential minus initial value of the potential. So it will be Q V final minus V initial, and it is equal to Q times delta V. And that's at the end, that's our unknown. That's what we want to find. Q times delta, oh, I mean delta V. Okay, so now I'll look at the ends, right, and solve it for delta V. So delta V equals that Q will go here into the denominator next to 2. So it will be mv naught squared over 2 times Q. Immediately, first kind of, how come? In the conceptual analysis, we got the delta V must be negative. But we're getting here, it looks like we don't have minuses. But charge is negative. It's an electron, right? Q is negative. Of course, mass of the electron is positive, square of the velocity positive, but charge is negative. Right, so let me emphasize on this. So Q equals minus 1.6 times 10 to the power of minus 19 coulombs. So that's the charge. Again, mass, open the book, you can get it. And so the answer will be, or maybe I will write it. So 911 times 10 to the power of minus 31 kilograms, that's mass. Then square of the velocity, 500,000 meters per second squared, and divided by 2 times minus 1.6 times 10 to the power of minus 19 coulombs. Okay, probably I should erase this since I decided to write numbers. So delta V is minus 0.712 volts. Again, it's like in a previous recitation class, right? Very similar, except for now, every time we have to use this potential energy equals charge times the value of the electric potential. Otherwise, structure of the solution very similar using energy approach. Oh, we need to speed up a little bit so that we can finish at least this problem. Next one. Okay, I will erase this. Right. You know what? It's fine. That's why I like to have more whiteboards so I can keep stuff so that I can compare reference to something later. So now we separate this, and it's a 2543. 2543. So we have a proton now flying through the through some electrical ore, which is described using some information about the electric potential. So let's assume that there is an ore, electrical ore, and we have only information about the electric potential along these lines. So these are equipotential lines. And what do we know about these lines? That these all points on this line is at 30 volt potential. Then this is at 10 volt, and these points are at minus 10 volts. Then this proton flies through this area. So let's say it travels this way. So it's a proton. And let's introduce 2 points. This point, let's call it point A, and this point, point B. And let's say we know that velocity of the proton at this point A is V sub A, and it's given. V sub A is, I don't remember the number, 50,000 meters per second. So now we need to answer the question, what will be the velocity of this proton at point B? I know, charged particles flying from the sun, solar wind, getting into some electric field, right? So, situation which is not unusual. Same note. Guys, if there are some issues, it's better if you just say it, because I cannot check chat all the time. Is it okay now? Is he frozen? Because I see the discussions.
For me, I can't see the updated discussion, but I can see you now.
Ah, okay, okay.
Yeah, I think it's working now.
Mm-hmm. Okay, cool. All right. So which approach to use, energy or force approach? Definitely energy, because in order to use force approach, you need to know information about the electric field. We don't have any single information about the electric field. We barely have information about the electric potential only at these three lines. We can get, like in next class we will see that we can get some average information about the electric field, for example, between these two lines, but average things are not good enough for if you want to calculate everything exactly. So in this case, we must use energy approach. It's the only one because we don't have enough information to use the force approach. There are situations like this, right? So the second approach is just you cannot apply. Right. So again, I will use energy. So it means that we can compare total mechanical energies at 2 points A and B now, not initial and final, but since we label them A and B, so. And so now explicitly, kinetic energy plus potential energy equals to kinetic energy plus potential energy, but now at point B. And again, we will need that formula which I just erased. That's why I don't like erasing the review, because every time I refer to that. All right, so QV, right? So of course, over here I'll have to insert the total, the potential energy equals the charge times the charge of the proton now, times the value of the electric potential at that particular point, right? And so what we need to find VB, so our unknown is here, right? So let me move terms around. So QB, so that's where unknown. This term I will move to that side with minus, so it will be KA plus UA minus UB, right? And now, only now let me write everything in terms of velocity and the potential. So it will be 1 over 2 mvb squared equals to 1 over 2 mva squared. So you see, basically, again, the same total mechanical energy, and then the same steps, almost the same steps. But now none of these terms is zero. Disappointment, right? So then plus QVA minus QV sub B, right? Again, now like in the previous classes, let me, this is our unknown, right? So let me free it from this factor. So in order to do that, let me multiply it by 2 and divide it by m, the whole equation. Each term multiplied by 2 and divided by m, so that I can free this unknown. So as a result, I will get VB squared equals to VA squared, and plus Q I can factor out. So it will be 2Q over m and VA minus VB, right? Okay, now I'm lazy to rewrite it, so I will use my eraser. I will just remove this factor of 2 and put a square root sign. Okay, yeah, you can plug numbers, right? So the only thing, let me emphasize on this, right, so that you would make some silly mistakes. Minus from the formula, from the expression which we derived, and minus because the electric potential at point B is negative, right? So it will be what? 30 volts minus from the expression, and then minus 10 volts. So it will be, of course, 30 plus 10. So if you plug numbers, you will end up with VB equals to what? 1 times 10 to the power of 5 meters per second.